All right, hello everyone. We're going to look at section 7 here, which is focused on the Neyman Scott problem. We just went through this exact same case actually in section 6 we went through a simple version of this case. The Neyman Scott problem is a term for a general case when maximum likelihood estimators are inconsistent. They don't converge to the thing that they are estimating. And so we're going to look at a particular case just to fix these ideas and see why that intuitively is true. That's all this is. This will be not too long, I hope. So the Neyman and Scott problem, the reason it's called Neyman and Scott problem is because they were the first to show that maximum likelihood estimates could be inconsistent. So everyone thought, oh, wow, you have a function. It's, that function has some parameters you're interested in. You just pick the value of the parameter that maximizes the function because that's what you want to do. It's a little bit like you have an objective function, or I'll just pick the value of the functions that minimize that function, of course, because that's what I want. I want the minimum function. Well, that doesn't mean you always end up with the right answer. And it took a while. Maximum likelihood, the idea of doing maximum likelihood was around since, I don't know, maybe 1910, 1915. It took to about 1948 for people to say, oh, this can go wrong. This can go wrong when your models get complicated. Okay. And the key to their example is that the actual model changes as the data accumulates. And this is how I think about it in a statistical sense. In a machine learning sense, this is not always as helpful because there are so many parameters. It's hard to tell what's changing or not. But the basic theory of maximum likelihood assumes that the model remains constant. It assumes that the model that's generating the data is indeed constant. So let's see what we mean by that. So how does this work? All right, so I have here now, and we're going to go through the basic idea. And we looked at this situation already. And we used X's before, so now I'm going to switch. I'm going to use Y. It's a little healthy to try different things. Y1 through Yn are normal mu sigma squared. And the maximum likelihood estimator of the variance is this thing, okay? And of course, the maximum likelihood estimators are biased. Hold on. Okay. All right. And our bias. So we just saw this in this case. Notice here that I'm using lowercase y's. I could actually use uppercase y's to be strictly better, but it's okay. The expected value of the maximum likelihood estimator is this thing here, which is this, and then we just talked about this. So the bias is minus sigma. We just talked about this in the last recording, which I recorded just a few minutes ago. So the bias is minus sigma squared over n, and when n equals 2, this is a whopping 50% that you're off. But so what? The bias shrinks as the sample size grows, and this goes to 0 rather quickly at the rate of 1 over n. So when n equals 10, the bias, right, is minus sigma squared over 10, which is, now we're starting to get smaller, right? Smaller. And we know that the limit of the expected value is sigma squared, or of course that it's going to end up in the right place because the bias is going to 0. So essentially what we're saying is, hey, here's this case. This is equal to my target plus a little bias, and then this bias is going to 0. So no problem, right? No big deal. Well, this will become a big deal if, in fact, your sample size never gets big. If your sample size is always 2, you have a problem. We, of course, get in the habit of looking in the case when n goes to infinity. And what Neyman and Pearson did is they constructed a pretty clever example where it looks like the sample size is going to infinity, but it's not really. And in the past case, we saw that. In section 6, we had a case where we observed pairs of observations, and we were estimating the variance between the pairs. Now, the number of observations that we used to estimate the variance stayed the same at 2, because we were collecting pairs. Every pair is 2 observations. But we collected more and more and more pairs. So it seems like the sample size is getting big, but it's not getting big in the way that we need it. Let's take a look at what's going on here. So nobody generally runs around crying and screaming because with 2 observations, the maximum likelihood estimator has a 50% bias. Well, sometimes they do when you call it the Neyman-Scott problem, but we're going to ignore that. And so the Neyman-Scott problem is just this situation dressed up all very fancy. Okay. And we talked about this. It posits collecting groups of data, each with a different mean, but a common variance. And they show no matter how many groups are collected, the bias remains the same. And that's because the bias stays the same within each group. So if I collect 1 million groups of size 2, and I compute the MLE in each group, and I average those MLEs, then of course, the average bias is going to stay to be 50%. Because each of those estimates is biased by 50%. If I average my bias 1 million times, my bias doesn't go away. It stays at 50%. So that's what we get here. So increasing the number of groups doesn't actually help us estimate the variance because each group is centered in a different place. So doing 1 million crappy studies doesn't help you get a better estimate of the thing you're interested in. That's basically what's going on here. All right. Now, we know the true mean, without knowing the true mean for each group, it's impossible to combine the data in such a way that allows us to estimate a common variance with greater precision or less bias. Simply averaging the maximum likelihood estimators doesn't do the trick because each MLE is biased, and so that average remains biased. Let's take a look at the problem in general. I think it's helpful. Here's what our data looks like. Right? Each row represents a group. So this is group 1, and this is group N, right? So this is what we're doing. The columns represent the first observation. So this is the first observation in each group, et cetera, et cetera, et cetera. And this is the last, this is the kth observation in each group. Okay. Let's see. Let's see. We have K groups. I'm sorry. Let's correct that. We have K groups and we have N observations in each group. So now I am totally messing up the notation here. And observation. So in each group, we have N observations and we have K groups. K groups. N observations per group. So our model is still this normal model with the fixed variance, but a different group mean. And again, I can write down the likelihood function, which is the product of all of these densities. And I can write it down and I can get the first derivative and I can set the first derivative equal to 0. And that gives me this very nice looking maximum likelihood estimate. This is the MLE of sigma squared. What do I like about this thing? Well, it looks like it's an average over groups. So I have the sum, I think it's J over 1 to K. So I average all groups, and then I'm summing in each group the maximum likelihood estimator. So this piece here, this small piece, let's see if I can use it here. This is the group estimate of sigma squared. And then I average these things. And so if I get a crappy group estimate, averaging a crappy estimate a whole bunch of times doesn't make things any better. And so averaging is important, but it's only important when you do it in the right place. So now, if I fix the number of observations per group, this fixes the MLE bias because we've seen this a number of times, right? So if I have 2 observations per group, the bias is half a sigma squared. If I have 100 observations per group, then the bias is sigma squared over 100. which is small. So the key is in getting a good estimate. The key is not in averaging a whole bunch of poor estimates. So as the number of groups increase, say k goes to infinity, the bias in the maximum likelihood estimator remains fixed. Increasing the groups doesn't help you estimate. Look back at your data here, right? So I can grow my data this way. That doesn't help you because you need to grow the data this way. You need to grow this way to estimate sigma squared. Growing this way doesn't help because every time I add a new row, I have a mu1, I have a mu k. Every time I add a new row, I add a new mean. So I add something else to estimate, so it doesn't help. Of course, with a reasonable group size, this is not an issue. Maximum likelihood estimator was work well. So again, you need enough data. You need enough data in a particular way. When you have very complicated models, you need enough data to estimate all the parameters correctly, and you need enough data to identify the unique aspects of each model. If you can't do that, then you're not going to get much of anything. Some thoughts is you can't reduce the bias of your experiment by replicating it and averaging those replications, right? You can't make up for a lack of information about within group variation by collecting a little data from a lot of different groups. And then not everyone agrees that this is a so-called problem. It's called the Neyman-Scott problem. But it seems to me, and it seems to a lot of people, that this isn't a particular problem. This is just a function of not having enough data yet. So this is good. I'd be happy to discuss this with you. I mean, think this is an example that is particularly relevant for when you start learning from machine learning models, which have lots of parameters. It's not clear what those parameters are, what they're estimating, or even if you care, if you're only interested in the predictions, you may not care that those parameters are consistent for anything. So there's lots of discussions that we can have about the applications of this to the machine learning context, and I'll look forward to having those as we go through class.